Let's try another one. We're going to do the limit of e raised to the power x over x squared, and it's the limit as x goes to infinity. All right, so the very first thing we should do is just investigate what is the top term doing and what is the bottom term doing. So very first thing, we want to check the form. All right, so we're going to do the limit of e raised to the power x over x squared as x goes to infinity. And let's look at what the term in the top is doing. So what is e raised to the power x doing? Well, x is getting really big, really large positive, and e to the x then is also going to get really large positive. So the term in the top is going to infinity. Now, what about the x squared? So then we look at the x squared down there. Again, x is getting really large positive, so that means x squared is also going to get really large positive. And so we end up with this infinity over infinity form. It's indeterminate, so it's not the answer. We can't say what this limit is doing just by looking at infinity over infinity. So, this is never the answer. Infinity over infinity is never the answer unless the question is what's the indeterminate form. But in terms of calculating our limit here, this doesn't tell us anything, except that we have to stop with this, and we can use L'Hopital's rule. So, this is kind of helpful, identifying the form here, because it's of the right format now where we can use L'Hopital's rule. All right, so that's the next step. We're going to apply the rule. So we doing the limit of e raised to the x over x squared as x goes to infinity. And we're going to apply L'Hopital's rule. So that means we're going to differentiate the term in the top, differentiate the term in the bottom. We're still calculating the limit. All right, so our fraction was e to the x over x squared. And actually applying the rule means we apply the derivative to the top term, and we apply the derivative to the bottom term there. Then we're going to calculate those derivatives. So we've learned a whole bunch of techniques and derivative rules. So we have all of those at our disposal, but these ones aren't too bad. E to the x is just e to the x when we differentiate. And derivative of x squared is 2x. We have a brand new limit here. So if there were things to simplify, try to simplify them down. But we have this brand new limit to consider, so we kind of start the process over. So at this point, this is brand new. It's a brand new limit. So we almost start over. Think of it as like this is a fresh start right here. And so it's not entirely clear what the limit is. Can't just plug infinity in. So we have to look, well, what is the term in the top doing? What is the term in the bottom doing? So we kind of go through this check the form step again. And if we're looking, e to the x is still getting really big. 2 times x, well, if x is getting really big, 2 times x is also going to get really big. So we have another indeterminate form. Again, it's not our answer, but we can use L'Hopital's rule again. So that's kind of the third part of this, is you just kind of repeat the process over and over until you stop getting these indeterminate forms. So you repeat it as many times as possible until you get it down where it's no longer an indeterminate form and it's hopefully something you can do. So if we apply the rule again, so we're going to apply it again. So we'll put a little h there to denote we're applying L'Hopital's rule. And we're going to apply the derivative to, again, the term in the top and the term in the bottom. So we're applying the derivative to the pieces of our fraction there. Actually calculate the derivatives. So derivative of e to the x is just e to the x. Derivative of 2x is just 2, and we're doing the limit as x goes to infinity. And now you can see why L'Hopital's rule, why it's so effective, is A lot of times when we differentiate, the derivative simplifies. The derivative is simpler than the function we started with. So the derivative kind of, not always, but the derivative a lot of times gives us a simpler function to work with. And so you can see here, especially with this power function, we went from an x squared down to a 2x. Then from 2x, we went down to a 2. So at each step there, it kind of simplified a bit. And now we're at a point, this is a brand new limit, so we just start the process over, and e to the x is getting really big, and then we're just dividing a really big number by 2. We still have a really big number. So if you want, you could think of this as we're taking e to the x and we're multiplying it by 1/2. You kind of want to rephrase it like that. And so if x is getting really big, e to the x is getting really big. And then we're multiplying it by 1/2, but the result is still a really large number. And so this is an infinite limit. So we get it to a point where, this e to the x over 2 is like, it's an infinite limit. It's not an indeterminate form, so we actually know what it's doing. So there we go. We have our answer now. And so this is an example where we had to use L'Hopital's rule twice. Each time we checked that we had the correct form before we used the rule, and then we just indicated where we actually applied the rule. All right, just practice these, a few more of these.